Okay, test for the people at home. Can you hear me at home? Can the people at home?
Yes.
Thank you very much. Thank you very much. And we just take some time. I have to prepare all the material. Thank you. So we start in 5 minutes, okay? So I will start at 3:08. Let's put like a 10. Okay, I see 17 people. 17 people online. I see. Due, 4, 6, 8, 10, 12, 14. Yes, we are still roughly 50-50, 20 people online and around 17 in the classroom. Let me check. Okay, I'm using Jabra Speak here. Let me check Panopto. I'm using Jabra Speak. It should work, right? Okay, so I still have to wait. We start at 3:10. Okay, it's 3:08 makes no sense. So I go to get some water. Okay, so welcome to the class of Applied Econometrics, second week, Monday, 21 February. Okay, still, let me check that everything works. It seems that the recording mechanism is working. Okay. And this is so I see 28 people connected at home, and well, okay, quite less from the classroom. I count 21 from the classroom. Anyway, this is the program I'll follow today, the organization of our class. So I'll be teaching until 4 o'clock, then we make 15-minute break, okay, until 4:15. Then we still we continue our class until 5 o'clock, and 10-minute second break will be a little bit shorter, 10 minutes, because then I would like to stop at most, even say before 5:50. And that is the end of our class. So before I start, I'm asking whether there are questions, clarifications, before we start, whether there are some questions from the audience. If you need some clarification on what we have done today, otherwise I will start. Okay. So if there are no requests from the audience, let me make very quickly the point. We are working basically, we are in this area here of our program. What we have done, we have been discussing what a classic linear regression model is, and we know more or less what the OLS estimator is. Then today I will start exactly from here, from the derivation on how we obtain the OLS estimator in the classic linear regression model. So I will repeat very quickly what a classic linear regression model is, and then we'll say something about the generalized linear regression model, which is quite a generalization of the classic that we know very well, and then I will say something about when we estimate a model with robust standard errors, the meaning of that. And of course, I will follow in parallel this theory with some Gretel stuff, okay, that we'll do together. So I go I come back on our slides, and in particular, I go to this. Very quickly, I want to come back on very quickly on this, on the matrix form representation of the linear regression model we have been discussing, this way, which is an alternative way relative to using indexes, okay? And we have to know that the two things are perfectly equivalent, but it is convenient. Sometimes it is convenient using one notation, sometimes it's much more convenient using the other notation. So the very important things are, okay, we have this representation, and the big sigma matrix has an important role, because we said when we have some condition where, according to which the big sigma is a diagonal matrix with elements on the main diagonal equal, so equal elements on the main diagonal, it means that we have homoscedasticity and we have, of course, some correlation. And then in the other cases, we have a complication relative to case number one, which is our case of interest. And case one is the one which refers to the classic linear regression model. So classic means homoscedasticity and correlation. Then, we know everything up to this point. Now, we have this model. So, linear, of course, I'm not mentioning, because we did a lot, we did the job last week, that we are working under, say, a particular interpretation of the linear regression model, which is not always obvious. We are conditioning, say, our knowledge of the endogenous variable, we are conditioning upon the regressors, on the X variables. This is a model for conditional. This part here in particular is a model for conditional expectation of the endogenous variable given the regressors. And under this interpretation, if you think about it, we don't care about the regressors. They're just condition. We don't need to model the regressors. And we said that under that, we know that under this interpretation, we have the implication of this interpretation is that regressors and the error term are uncorrelated. And we saw an example where this interpretation does not hold. And if you come back to the interpretation, to the example we did, you will realize that it is a model where we take a stand on modeling one of the regressors. Think about our example about our simply stylized model for temperature in Italy. If you remember the model, we have temperature depends on, say, CO2 emission. We said also depends on sea temperature, okay? Of course, I'm not an expert of this thing. This is just an example, okay? I am an economist, not, well, I am a macroeconomist, but not, I do not work. So my example could be a naive one, just to clarify. So what I did say, if we have some argument you have some condition to claim that, say, sea level shocks to the sea level temperature are somehow correlated to shocks to weather temperature, we have basically we are seeing that the interpretation we are working on does not longer hold. And we'll see, I hope that maybe tomorrow we'll see which are the consequences of that on the properties of the OLS estimator. Okay. Today we will discuss about we discuss a few things, but in our next classes the focus will be on say dealing with the OLS estimator. But I'll bother you, not bother. I mean, we'll work a lot upon which are the properties of the OLS estimator, and we have to do that because the OLS estimator is not always blue as probably you might imagine. And so we have to know when it is blue and when it is not, if you want to understand how to model our phenomenon. Okay? So in this model, we have homoscedasticity and uncorrelation. We know that because the form of the big sigma is like this. This must be clear. And so the parameters, the unknown parameters, the guys I want to pick out from the data are the slope parameters in the beta vector, okay, and say the single variance of the error term. There is just one, and you know it's a huge simplification because now we have to estimate k plus 1 parameters. And if we have n observations, it's a job we can do. Okay. Now, how do we we said that the beta estimate, the estimator of beta is obtained by, we are using what we call a non-parametric approach, which means that we don't need any assumption about the distribution of the variables. We are making, when we compute OLS, we make no claim, for instance, about the distribution of the error term. But there are different estimation methods. Let me say, for instance, maximum likelihood, if you ever heard in your life about maximum likelihood estimation. In that case, you need an additional assumption. Other than homoscedasticity and correlation, you also have to take a stand about the distribution of the error term. We don't need that with OLS. So we stick to a very simple way, and you know, this Gauss was a genius, because mathematician Gauss the OLS is due to Gauss, Frederick Gauss. So the idea is very simple. I want to minimize. I have this. My objective function is the sum of square errors. Okay. I want to find the beta which minimizes the sum of square errors. One might say, well, why should we go for squares? You know, during when Gauss lived during 1840, during that times, I mean, it's not. They do derivatives by hands. Do derivative of square is quite easy. But I could take, for instance, an alternative objective function. I could take the absolute value rather than the square, absolute value between the true and the predicted one. In that case, I get an alternative estimator. This is a very intuitive one because I want to minimize the sum of squares, okay? And this equals to, if you have understood, if you have done what I suggested, that is studying the relationship between this notation and this notation here, you realize that this minimization problem is equivalent to this one, okay? So I have matrix representation here, I have indexes here. Now, after solving this problem, we get the expression of this, the beta estimator is given by this expression here if I want to go for matrices, and this expression here if I go for indexes, okay? From a point of view, if one day you have to write your program in a matrix-oriented language, this is once you get the X matrix, once you get the Y vector, this is just very simple to say, well, beta at is given by this expression. If you don't know this, and if you know the notation using some measure, you need a for loop. For I which runs from 1 to n, do this. You know, it's much more efficient this way. Anyway, in order to compute this estimator, you understand that you need the X prime X matrix, which is K by K, must be invertible. So the condition that I need for that to hold is that the rank of the X matrix, recall that the X matrix has n rows, n is the number of observation, and k columns, k are the k regressors. Basically, for each column, in each column of the X matrix, I have observation, n observation on regressor 1, 2, 3, blah, blah, blah. Okay? So I need, claiming that I need the rank condition, the rank of X must be k, it means basically that the k columns on the X matrix must be linearly independent. Otherwise, it would mean that, say, the information provided by one regressor is already contained in another regressor. So if I have this condition, it means that the information on regressor 1 is completely I would not say it's linearly independent from the information on of the second regressor, and so on. This is an important condition. If this condition does not hold, you're not able to compute the OLS estimator, okay? And your package will say, oh, I have some problems. Now, how do we solve the minimization problem? I don't want to bother you that very much about computation, but I need to give you the sketch, okay, of the proof. So you know how to optimize functions from Professor Dieci course. So what we have to do, this is our objective function. You know that when we're looking for a minimum, so I need to compute the first order condition. I have to compute the derivative of my objective function with respect to the vector beta. Beta is not a scalar, it's a vector. We're simply generalizing things that we should know. But if we don't know, it's not a very it's not a complication. Okay. So we put the first derivative equal to 0. Those are the first order condition. What is the meaning of computing the derivative of a scalar objective function, because QB is a scalar? Why is it a scalar? Because it is defined like this. It's just the summation of scalars. Or this is a row times a column. And you should realize that if I multiply a row times a column, that is a scalar. It is the other product, okay? So I need to compute the derivative of this function with respect to beta, which means I need to compute from a mathematical point of view, would mean the derivative of the first of the objective function with respect to the first parameters, second parameters k. Okay, but it is not convenient going on this way. It's much more convenient applying the rules of the algebra. So you don't need to now. You have to understand what you find in these slides when you come back home, when you study. Now you have to follow my reasoning. So this derivative is the derivative of this objective function with respect to beta. So what I have done in the numerator, I expanded the numerator. I multiplied this guy prime times y. I got this one. Then I multiply y prime times this guy, and I get this one. Then I did also, I multiplied this one transposed by y, and I understand that it is exactly equal to the previous term, so that's why you find 2 here. And then finally I have this guy transposed times this, and I get this number here, okay? So recall that the parameter is beta. So the first term, you know, the derivative operator is a linear one, so the first term doesn't matter, does not depend on beta, so I can kill the first derivative here, so you don't find it here. And then you will find -2, and then I have the derivative of this object here with respect to beta. And you know, this is a linear, imagine that beta is a scalar. You immediately understand that this derivative will be this number here. I don't need to think too much about that. Think about the second the derivative of this term here now. Imagine the case where beta is a scalar. So you would have beta squared. What is the derivative of x squared? Will be 2 times x. And it is exactly what I get here. So I'm generalizing rules that you know very well to the vector matrix case. But aside from that, nothing new here. And then, so look at this expression here. This derivative equal to 0, first order condition. I realize that I have 2 here. I have 2 here, so I can simplify. I can kill the 2. Okay. I bring this guy on the right hand side, so I will change the sign, so the minus disappears. Okay, guys. And finally, I have something like x prime x beta equal to y prime x. So if this guy x prime x is invertible, condition I said here, if the rank of x, why is it important this condition here? Because if the rank of x is full column rank, it means that x prime x is invertible. So I can solve by this expression by simply, I invert this matrix, I get the following expression. Very simple. There is nothing to understand. There's just to know to apply some rules. And you have the rules here and here. This derivative is this object. The second this derivative here is this object. Okay? And the question was, we already discussed that last time. We don't need to make a check on the second derivative, because we know that this guy you have here. It's a parabola. So we have a parabola with concavity towards up. Okay. So I know that I'm looking for a minimum. Okay. But if you do second derivative, you could apply. If you do second derivative, you immediately understand that this term, so I have to take the second derivative with respect to beta to this guy. So the first term, the one selected, disappears, does not depend on beta. And you should agree with me that if I do the derivative of this term with respect to beta, I end up with x prime x. And x prime, given any matrix, full column rank, and you compute x prime x, that matrix will always be positive definite, which means that we are computing a minimum. You know, the rule is, when we are looking for the optimum on objective function, you do first derivative, put it to 0, find condition, then second derivative, you evaluate second derivative to the optimal point. If the second derivative is negative, you have a maximum. If it is positive, you have a minimum. So if you do second derivative, you get x prime x here, and that is a positive number. It's not a positive real number, it's a positive matrix. We are simply generalizing, okay? Now, second step, once we get the beta, remember that we are looking for estimator of betas, low parameters, and sigma square epsilon. Don't forget about sigma square epsilon, okay? So which is the estimator of the sigma square epsilon is given by this expression here, which is kind of, look at it, just intuition. Imagine for the moment that we are dividing just 1 over n, kill for the moment minus k, okay? It would be, think about this term here. Now, the guy you have inside the parentheses, true value minus x prime beta hat. Now, this distance, this is a residual. This is epsilon I hat, which is what you find here, okay? And squared. So it is kind of average. It is a kind of average of square residuals. The reason why we divided by, of course, if you are dealing with a large sample, divided by 1 over n or 1 over n minus k doesn't matter if n goes to infinity. In small samples, it can make a difference whether you divide by 1 over n or 1 over n minus k. But there is, let me give you just the intuition why we divide by n minus k. In a sense, in order to get this estimator, we already estimated beta, which is k by 1. So we already estimated k parameters. So I want to say, I want to ponderate, I want to divide this sum by the number of observations up to the parameters I have estimated. This is an argument by statistician, but we'll understand why later on. But this is just a rule, okay? And if you have understood the rules, the connection between index notation and matrix notation, you realize that this expression here is the same as residuals prime residual, but this is a vector now, and it is equal to this expression. Okay? Before we discuss the properties of the OLS estimator, which is, let me stress it several times, it's not always blue. It is blue under some conditions, but not always. We'll see that. But there is a very important point that I want to stress all the time we do OLS regression is the following, that all the time we apply OLS, we have in mind a situation where the correlation, I'm coming back to our to something that I already said, but now it is even more important to come back on it. I mean, we are dealing with a situation where the covariance between the regressor and the error term is equal to 0. Okay, this is an uncorrelation or orthogonality conditions. We have to verify. We have to for the OLS to work, and you will realize that very quickly, that we need uncorrelation between regressors and the error term. And let me say that why this condition is in line is not at odds with our interpretation, because if you compute this correlation by applying the law of iterated expectations, something that we're going to use in a very intensive and extensive way, okay, I realized that if I can claim all the time, I can claim that my forecast of the error given the x's, given the regressor is equal to 0, then I have this condition, this uncorrelation. And now my point is that we already have seen an example in which, for instance, this is different from 0, our example about temperature. And if you think seriously about a phenomenon, you will discover that in many times you will have doubts about absence of correlation between regressors and error term. But we'll come back on this topic. Now, the properties of the estimator of beta and sigma square epsilon depends on the context. So that's why I'm not claiming that it is blue. We typically distinguish between finite sample properties, which are the one that we refer to when n is treated as fixed. So think about our example about the 20 Italian regions. In that case, I can hardly claim that n goes to infinity. Of course, if I'm dealing with 20 million Italian households, if I have a model for Italian households, yes, I can send n to infinity. But if I'm dealing with 20 Italian regions, no, I need to stick to the finite sample properties of my estimator. Okay? Questions, clarification, please interrupt me. Also, Tom. Okay, guys, are you following me, Tom?
Yes, we are.
Okay, very well. Let me make a check about recording, whether it is working. Okay, it seems there is no warning from Panopto. Okay, Salvatore, can I go on? Yeah. Can I safely go on? I go on. Okay, now, so the properties depends on the context, and so we distinguish in general between finite and large. And we have discussed these properties on a case-by-case basis. So I have to bother a little bit here, okay? So finite sample property are the one when we saw the blue conditions, and my claim in this slide is that the OLS estimator is blue only in very special cases. I will discuss. For the moment, we can skip the second line. Let me go to the. Okay. Let's second line. Second line claims beta hat sigma square hat is blue when the regressors are not stochastic. Very rare. Very seldom in social sciences we can claim that the regressors are not random variables. So this is typical of the sum of the experimental context, where you can keep x fixes and you see what happens to y. But that is not our case. I cannot assume that whether C temperature is fixed and I see the response of, say, outside temperature. They just are two random variables. They move simultaneously. So no way of doing some. My regressors in our setup will be realization of random variables. So this second case is a wonderful case of experimental context. Unfortunately, it's not our case. Okay. Now look at this claim. The OLS estimator beta hat sigma square hat is blue, so best linear unbiased when the x are stochastic, so our case. And we have cross-section data. This is very important to keep in mind. In particular, in cross-section data, we can claim we have this condition. This is very important to keep in mind. What you should change in this slide is that this expected value, not of u, epsilon. Sorry for this. You should change this u with epsilon. Okay. I can I do that? Let me check. Okay, but okay, this should be epsilon, the epsilon vector, okay? Given the X matrix is equal to 0. We have to work on that, to the meaning of this thing. And but when we can claim that the expected value of epsilon given X is equal to 0, then we can, you know, the arrow means the implication is that we can prove that the expected value of the OLS estimator conditioning on the X is equal to the true beta. So we have unbiased, okay? And we also can prove that, we don't prove it, we take it, it's also the best. The OLS estimator is the one with the minimum variance. One situation where, now let's go to the novelties. One case where the beta OLS estimator is no longer blue, so in particular is no longer unbiased, is this situation. Imagine that the X are stochastic, our case. We have time series data. Think about, say, the example where on our weather temperature, okay? But among the regressors, we have, say, legs of the endogenous variable. So do you remember the example, for instance, I tend to confuse, to mix up classes, you with the other one I'm teaching this, you know, so I don't remember if, probably Salvatore can help me, but okay. Okay, doesn't matter. So there are cases in which we'll see example where, again, this is not, this one should be epsilon, not u. Sorry. Again, there are situations where we see that the expected value of epsilon, epsilon given the X is different from 0. So we have different case relative to the previous one. So in this case, we have the OLS estimator is unbiased. Is biased, sorry, has a distortion, sorry, okay? It's different from the true value, beta. And so I want to, the writing, the expected value of some random vector given the entire X matrix deserves some special treatment. I have that in the blackboard, and this is probably not what I want. But I'll come back on that. We'll see when we discuss seriously the properties of the OLS estimator. We'll see the differences between this condition here and this condition. When do we have this? When we can claim we have this, which is the cross-section data, and we'll see that when in our regressor we find some regressor, the endogenous variable t minus 1, we will see that this condition, this expected value is different from 0, and the main implication is that the OLS estimator will be no longer centered on the true value. But we'll see that in that cases, we'll discuss other properties of the OLS estimator, which are the asymptotic ones. When we can claim that n is large, we can skip the finite sample properties, and we can focus on the asymptotic. Is not, it's a word that apparently scares us. No worries. Just asymptotic means large sample, okay? And so you are not scared about the word, okay? And the properties of the estimator we look for when we can claim that n goes to infinity, when we can approximate n such that n goes to infinity, are consistency and asymptotic normality. Consistency and asymptotic normality can be valid also when the OLS estimator is distorted in a finite sample. That will be the point, is that the OLS estimator, even when it's not centered on the true value, But if we are in a situation in which we can send n to infinity, the distortion disappears in some sense. And we have to, we'll work about considering, discussing this situation, okay? Now, in words, what is the meaning of consistency? I'm not going to formalize for the moment, just in words, okay? I say that the beta at estimator, and also the same applies to sigma square epsilon, is consistent if, say, the probability that my estimator gets closer and closer to the true beta, to the true value sigma square epsilon, this probability converges to 1. So consistency means that the probability that the distance between the estimator and the true value gets smaller and smaller, this probability goes to 1. So in a probabilistic sense, I am certain that my estimator is picking out the true value of the parameter, if I'm dealing with a large sample, of course. It is a very reassuring property, and let me say that if you have an estimator which is not consistent, the estimator is completely meaningless, okay? So it is crucial because without consistency, the estimator cannot be used, because you have a condition where the beta at converges to something which is not the true value you want to pick out. You want to infer from the data. You are inferring something which is completely wrong, okay? And there are cases where it is very important to know, whether my estimator is doing a good job or not, okay? Especially if I have to take policy decisions. Asymptotic normality, in words, it means that the distribution, the probability distribution of my estimator, when n goes to infinity, approaches the normal. So that's why you should know, from the crash course of econometrics, you should know everything about the normal distribution, almost everything, okay? A necessary condition for asymptotic normality is consistency. So if your estimator is not consistent, it will not be asymptotically normal. And why do we care about asymptotic normality? Because if we have an estimator which is asymptotic normal, we can make inference. We can interpret, say, when Stata or Gretel or whatever gives you an output, the estimation output that we know, and you know that n is large, and we know, since we have been studying econometrics, we know that our estimator is asymptotic normal, we can use the property of the normal. And when we can use the property of the normal, we are happy, because we can do whatever we want. We can test hypotheses, we can build confidence intervals, we can measure the impact of GDP on CO2 emissions with an confidence interval, and with a reliable confidence interval. Finally, asymptotic efficiency means basically that the standard errors I have for my estimator are the best I can get. Okay? So I will be very fast about it. Now, we have derived the OLS estimator, but I said it is important that we know the properties of the OLS estimator, and think about, say, when we say blue, we means the U stands for unbiased, okay? The true value is centered. The B of best means I'm looking for the estimator with smallest variance. I want an estimator which is the most concentrated around the true value. So it's by using, I present that as an exercise. It's possible to prove that the variance of my beta estimator conditioning on X is given by this expression. Now, is this exercise very impossible to solve. Let me give you just, I want to come back on that. I'll come back on this, but for the moment, take it as a formula, okay? The variance covariance matrix, because please recall that beta is a vector. So when I compute the variance of a vector, this will be a matrix, okay? What do we have on the main diagram? Take this expression as given, okay? So it is sigma square epsilon, this scalar, times x prime x inverse. You know, this x prime x inverse, we find it several times. It is exactly the same x prime x inverse we find in the OLS, in the expression of the OLS estimator. It's always is this guy, okay? So it's nothing particularly difficult to understand, okay? So my point is that if what do we have on the main diagonal of, this is a k by k matrix. Beta hat is a k by 1 vector, and its variance is a k by k matrix. So what do we have on the main diagonal of this matrix? Doug, don't be afraid to say, just interact with me, please. I can write vectors here, so I renounce that. But if you have a vector, okay, V1, think about a bivariate vector, okay, V1, V2, okay? And if I take the expected value of that vector, you understand that I'm considering the expected value of V1 and the expected value of V2. Are you there up to this point? Now, I take the variance of this bivariate vector. So you should agree that on the main diagonal, I have the variance of V1 and the variance of V2. The off-diagonal term will be the covariance between V1 and V2. So coming back to our example, it means that on the main diagonal of this matrix, I have, say, imagine, for instance, that we have just two regressors, so two parameters. So beta hat is just beta hat 1, beta hat 2. So on the main diagonal, you have the variance of the estimator beta 1, and the second element will be the variance of the estimator beta 2. And the off-diagonal term will be the covariance between the two. So we understand that we need, say, to know whether the estimator is centered or not on the true value, but we also need to know how variable the variability of my estimator. Because imagine that I have an estimator which is centered on the true value, but it is very dispersed around the true value. I say it is quite useless one. We are looking for an estimator which is centered on the true value, but it is the probability distribution is very concentrated on the true value, which means that we pick out the true value. Okay? And so we need this expression here because it is our measure of how concentrated or not it is our estimator. That's why we care about it. That's why I want to pose your attention on that. And of course, the column standard errors we have on Stata, Gretel, blah, 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 are taken from the main diagonal of this matrix. Once you replace sigma square epsilon with its estimator, the one I showed you before, okay, you can take the main diagonal of this matrix, you can take square root, and you get standard errors. And standard error, so it's a measure of the variability of my estimator, and that is it is crucial for me to understand whether I can rely or not on my estimates. Okay? Now, indeed, this quantity, this one can be estimated. The natural estimator will be, I replace the unknown sigma square epsilon with this guy here. And if I take the square roots of the element of the main diagonal of this matrix, those are the standard errors that any econometric statistical package reports. More precisely, let me be more precise, then we'll go to also, we'll see, you know, when I go on Gretel, I will make a parallel. So this is not just a, well, I would like to see things, I want to see a more practical thing. You will see the more practical thing. But before I need to tell you the theory behind that. Then we'll see also the practical thing. Now, so the standard error of, let me take, say, the element J of the beta estimator. So I take beta hat J. The standard error is defined by construction is the estimated sigma epsilon. And what is the symbol? What do I mean by C at JJ? I means this will be the JJ element on the main diagonal of the matrix X prime X. It's not difficult to understand this. And sorry, there is also, there is a mistake here. This is without square here, sorry. You have to kill, let me select it from here. Qui?
No, destra. La mia destra.
Questo?
Sì, poi fa...
Ok, evidenzio.
X.
Ok. No, not this. No. Okay, you have to kill the square I'm selecting, I'm touching with my hand, okay? This guy. Because I'm taking the square root of the main diagonal of this matrix. So this square here, the one I'm touching with my hand, must be killed. This one? No, this is a sign to. I don't need to add anything. Oh, okay. No. Anyway, this guy. Okay. So when we think about any estimation output, I'll see the example very quickly. I'll come back on our example. You have the column standard coefficient. So the coefficient will be the beta hat. And you will find the second column, which is standard errors. So it is, you see reported this guy up to this square, which is not here. Okay. And then you will find the third column, the T ratio column, will be the following ratio, say, the ratio between the estimated parameter over the standard error. And you now immediately understand that the larger the standard error you find in the denominator, the lower will be the T ratio. On the other hand, the smaller the standard error, the larger will be the T ratio. So we are putting, say, we are comparing an estimate with, say, the precision by which we estimate that number. So if we have, say, if I estimate this number 0.0 and I have a very large standard error, a very large variability, which means a very low T ratio, I don't trust that estimate. But if I have, say, 0.5 and have a very precise estimate of the variability of my estimator, so the T ratio will be a very large one, I trust my estimate. Now, but let me say that we'll discuss tomorrow, we'll go in a very, say, more intensive way on the properties of the LS estimator. Now I want to discuss you which is the difference between, I want to, let me go on what is a generalized linear regression model. So let me go to the classic linear regression model and the OLS estimator. So we have been seeing very quickly the OLS estimator, and what we are seeing today is, and then I'm going to stop, okay, according to the program. We said the OLS estimator, okay, we look for both finite sample properties and large sample properties. We discuss this property case by case, but the OLS estimator, we also have to consider the variance covariance matrix of the OLS estimator, which is because it is very important to have also the estimate. We have to associate the estimate with a measure of variability of our estimate. And for the moment, we can stop here. We take a 15-minute break, and then we'll start with the generalized linear regression model. So we are moving from the classic to the generalized. So break, we start at 4:15 according to our program. I'll write it on the chat. And I'll start in time, perfectly in time. Let me check if Panotto is doing well. He's doing well. If I put in pausa, then I can forget to so I let it go. It doesn't matter when you it's up to you to say to moving. Okay, we are ready to. So before I go on, I said, okay, we are now moving to here, the generalized linear regression model. And let me say that for the moment, I've said anything about the OLS estimator. I have a path to follow. So we are still up to discuss the properties, testing hypothesis. You will understand. I want to be clear before I move on, before I go on with the program, which the next topic will be the generalized linear regression model. Let me come back on our example. I want to show you up what we did last time. Okay, let me increase the font. I should set it in English, first of all, for preferences, generally, English, not automatic, I want English. What is it? Thank you. Okay. And now I have to close it and start it again. Now it will be in English. Let me check that. Okay, now I increase the font, tools, preferences, font scale, especially the student bot at home or not, let me know. Okay, should be better now, okay? But let me know at home.
Yeah, it's better.
Okay, thank you very much. So if you remember last time I discussed a model. We imagine that I want to quantify, say, the impact of regional per capita income on regional per capita consumption, because I would like to study what might be the impact of, say, regional tax. In this setup, we have 20 Italian regions. So if you remember, we estimate a model by OLS, ordinary least squares. Very simple way to move on in Gretel. I simply have to select the dependent variable with arrows. Regressors, I have a constant and income. Okay. I click OK, and I get the following estimation output. And now, what it is important, this estimation output, is to say that we have, say, the column coefficient. This will be the beta hat. This will be the realization of the beta hat estimator. The estimator is a random variable. Our random variable, given our sample, takes the following value. And the second column you find here, it's the column, the standard error. We have been discussing. I've been discussing before the break about standard errors, and then you find the column T ratio. T ratio is given, it's the ratio between the estimated over the standard error. And I said it is a measure of precision. One question during the break was, okay, what is the cutoff value of T ratio in order to decide whether the answer will be, you will find the answer in the last column, the p-value column, and we have to work on it. I can give you mechanical rules. For instance, I can say all the time you find that the T ratio is in absolute value larger than, say, 2. Okay. You will find in the column p-value some stars, and the stars means that you basically, the ratio between the estimated coefficient and the standard error is quite good, so you can rely your estimate. But this is just a mechanical rule. I don't want you to follow mechanical rule. I want you to understand what's going on here. So I want you to be conscious about the meaning of how to interpret this column. And I need some steps in order to arrive to that. And the same, for instance, about this F test you find here, F with a p-value. We have to learn about or how to interpret this guy. You will see, and I repeat it again, that the R-square number that you find here is important, yes, but not as much as you think. The R-square will be important when we have to compare two models which have the same dependent variable, where the dependent variable is written in the same way. In that case, the R-square makes sense. Otherwise, in absolute value here in this model, R-square 0.86. Well, it's good or not, I really don't know. It's not what I look for. Is not what I look at in order to evaluate whether my model is good or not. But one thing that my first check will be, for instance, since we know that when we do OLS, we are in the condition where the big sigma matrix is homoscedastic. So we have homoscedasticity. My first concern in this model will be to check whether homoscedasticity holds or not the R-square. R-square is just an index, an index, which can be, I can rewrite this model, the same model, such that the R-square, the same model, I can do some algebra in the same model, some transformation. I re-estimate the transformed one, and the R-squared could be 0.20, the same model. So I am concerned about whether the properties behind OLS are supported or not. That will be my first concern. And so in the path I am following to bring you this awareness, this to be conscious of what you're doing now, I have to meet this. We have to move from the classic to the generalized, okay, linear regression model. The generalized regression model arises all the times in which the big sigma matrix is different from diagonal with equal elements on the main diagonal. So for instance, imagine that you have uncorrelation, but you have heteroscedasticity in your model. We are in a generalized linear regression model. And in this case, the unknown parameters, the ones we put in the vector theta for us will be the vector of parameters that we want to pick up from the data, okay? So we still have the beta, the slope parameters, but now I have also some elements, the non-zero elements I have in the big sigma matrix will be also parameters that I have to estimate. Now, follow me, this is very important. Imagine that I have a model with heteroscedasticity. I'm in my model of 20 Italian regions, and I am imagine that I am pretty sure that I have, say, the 20 Italian regions have 20 different variances of the error term, because I could say there is so fragmentation among it. This is just an hypothesis, okay? I'm not claiming that. One might say there is a lot of fragmentation between the regions, especially between the north and the south. So I have very good argument to claim that, say, the variability of consumption, or what remains of consumption once I explain consumption with income, what remains depends. It's region specific. Depends on the region. So I don't believe that homoscedasticity works for the 20 Italian regions. So I imagine to have 20 different variances. So in that case, the parameters of my model will be the two elements in beta, because I have the constant and I have per capita income, plus the 20 variances I have on the main diagonal of the big sigma matrix. So I need to estimate 22 parameters, okay? But I have only 20 regions, 20 observations. So typically, in this case, in the generalized linear regression model, if I don't make some important assumption, I am in the situation where the dimension of parameters will be larger than the number of observations. So it will be impossible to estimate the betas and also the non-zero elements of big sigma. I am in troubles. And this is a generalization, simply generalizing the model. It can be reasonable assuming that I have 20 different variances in the 20 Italian regions. Now, so in order to, I need some assumption. For the moment, we make a very, if I'm faking a little bit, I assume that I know the big sigma. I know the variances on the main diagonal, which is not true, of course, but let me simplify for the moment, okay? If we know the big sigma, then I can still derive the generalized least square estimator of beta as follows, okay? I still have to minimize the distance between, the y's and the x beta. So I'm looking for the beta which minimizes quadratic distances. But now, relative to the OLS case, in the OLS case, you don't have the inverse of the big sigma here. So the big sigma now is playing a role, okay? And it enters this expression like the inverse of the big sigma. Then I'll give you, now in a couple of minutes, I'll give you the intuition behind this expression. Now, if I want to write, since all the time, I stress it all the times, both matrix notation, and indexes notation. If I go to the indexes notation, what I'm considering, this objective function here, the one I'm touching with my hands, with my virtual hand, is given by this double summation of what? I have some coefficient psi ij, which is kind of weight. I'm giving some weight to what? What is this? This is the error. This is the epsilon I times epsilon j. So I am considering all interactions between the errors in my model. So I can also have a situation where I and j are the same index. So I could have epsilon I squared. Okay? So I'm considering all squares and possible interaction of the error term. And you will find in front of each term there will be this psi, which is psi is an element of sigma inverse. Okay? So it is kind of weighted, it's a weighted sum of squares in some sense, and the weight depends on the inverse of the big sigma matrix. Let me give you the intuition. Imagine that the big sigma is, we are in a case where I have only heteroscedasticity. So I have, say, the off-diagonal terms are all zeros, and I have n different guys on the main diagonal, okay? So you should agree with me that if I computing the inverse of this big sigma metric is very simple. I simply have to take the inverse of all the guys on the main diagonal of sigma. Is it a statement that you can understand? Are you okay with this claim? The covariances are zero. I have only the variances on the main diagonal, and so inverting sigma inverse will be, say, I have a diagonal matrix, and on the main diagonal of sigma inverse, I have just the reciprocal of the variances. Okay? So in that case, look at this. Since I have all the cases where index I is different from j, the psi's are equal to 0 because it's the sigma inverse matrix is diagonal. And when index I is equal to j, I'm giving the weight, which is the reciprocal of the variance. So the larger the variance, the less will be the weight I'm giving to the term. That is that is why I call it generalized. I'm putting into play also the variances. And they play the role of weighting, guys. Okay? Those are weights. So the size are okay, I understand your question. Question will be, can we generalize, even play some weights, a matrix of weights taken from elsewhere depending on the context? Is that your point? Yes, the answer is yes. We can have also weighted least square, but I don't need in this setup now. In a sense, weighted least square is a special case of GLS, or let me put that way, GLS is a special case of weighted least square. But now I'm taking the weights from the variances, or covariances if I have. The important point you have to understand is that I'm considering double summation because I say the big sigma I could also have off-diagonal terms. But in the example I'm doing, just to simplify, imagine that the big sigma is diagonal. We only have heteroscedasticity. We have uncorrelation and heteroscedasticity. Case 2, coming back to our slides, would be this. Everything is always on the slides. So I'm taking case number 2. So you understand that if you invert big sigma, the inverse of big sigma will be 1 over sigma square 1, 1 over sigma square 2, blah, blah, blah. So the weights are simply these numbers inverted, the opposite of these numbers on the main diagonal. The zeros remain zeros. Okay? So to understand, the intuition is that we are weighting some way the square of error terms, okay? Now, if you go on, if you apply again the derivatives rule we have seen before for DOLS, so I don't need to do that because it's a useless exercise given our purposes, but at the end of the day, you realize that the GLS estimator is given by this expression here. You can see that it is very similar to the OLS. The only difference is that you find the inverse of big sigma entering here. With the OLS, you have identity here, you have identity here. Okay? Again, we need a full rank condition. Otherwise, this matrix cannot be inverted. And what I've written here is that the GLS estimator put like this is a virtual one in the sense that if you don't know the big sigma, you cannot compute it. So you can compute it only under very special circumstances. Okay? And again, as I showed you before, I said the variance covariance matrix of the OLS estimator is sigma square epsilon x prime x. In this case, by doing some computation that for the moment we can skip, you realize that this is the variance covariance matrix of the GLS estimator. And again, if you don't know the big sigma, you can't apply it. You can, I mean, you don't know what to do. Now, so the question might be, so what do you mean by feasible GLS? A feasible GLS will be an estimator where I make some claim such that I know something about the big sigma matrix. And I will provide you some example of it, okay? And in that case, if the big sigma depends, for instance, from the data, that will be a situation where we can compute a GLS, a feasible GLS estimator. Otherwise, we can't. So, but in order to compute a feasible GLS, I had to say, let's stick to the heteroscedasticity model. So let me come back to case number 2. what I have to do is, I should say, okay, imagine that I have an explanation, I have a model which explains why I have heteroscedasticity in my model. And which means that I have to make some additional assumptions, some additional hypotheses about these variances. But I will provide you with an example. Let me tomorrow. I'll provide you a concrete example. You know, according to my plans, I wanted to do that on the blackboard, but a true blackboard. This one. Look at here. Example of feasible GLS on the blackboard. It will be a virtual blackboard that we're going to discuss tomorrow. And a very simple setup is the case of per capita consumption, a model of per capita consumption. Now, what I want to discuss with in the next slide is the following object, OLS with robust standard error. And you will say, is it related to what you are saying here? Yes, it is related, but let me give you an empirical flavor again. Let me come back on Gretel. And this is the model I have estimated on with OLS. Imagine that I say, I want to re-estimate the model, and look at here, I have this option. Okay, sorry, edit, modify model. I want just to center, okay. I can flag these robust standard errors. Okay, I can click this, I estimate, okay, and I have estimated second model. Okay, let me check very quickly. Look at the column coefficients. In the two models, the two coefficients are exactly the same. Okay, so the beta has not changed. What has been changing is, look at the column standard errors here. Look at the standard errors here. They are slightly, they are not very different actually. They're not that different, but they change. And so, because of that, the T-ratio column, 7, 10, changes a little bit also here. But we are in a setup here where, say, making the option robust standard error and not robust standard error, you can see that the overall picture does not change very much. And let's look at an intuitive, let's take an intuitive interpretation of this. It means, I would say, just on intuition, that, well, if you flag or not, does not change very much, does not matter in your model. So it means that you can also skip robust standard error. And my question now, what I want you to understand now is what's the meaning of computing robust standard errors, okay? To be conscious, because I could say, mechanical rule, guys, all the time you find robust standard error, just flag it and you're okay. When you present your result, you say, I have robust standard error. But one day it happens that you meet one econometrician and say, okay, why did you select the robust standard error? The answer is, well, we all do like this. I don't want you to give an answer like that. I want you to give an answer. I have selected robust standard error because I do need robust standard error, not just because all the people do that. Okay? So, this is econometrics. Okay, so what's the meaning of OLS with robust standard error? Imagine that we are I have the suspect that I have a model like this. The big sigma is diagonal, but with different elements on the main diagonal, okay? So this is a situation which is different from the standard case, OLS case, okay? But the econometrician still applies, even the computational knows that in this case, the estimator it should apply, it is the GLS, not the OLS. We just saw it. But the econometrician also know that I haven't a clue about this number, sigma square 1. In our example of the 20 Italian region, this will be the variance of the error term of the region number 1. I haven't a clue about this number. I don't know this number. So what can I do? So the point is that, okay, you can still go on with OLS, but you have to be conscious of what is the price you have to pay going on with OLS. Okay? So the important thing to understand is we will be able to really fully understand this claim when I move in an intensive way to the properties of the OLS estimator. We can prove that even in this model, which is a GLS, the OLS estimator is still centered on the true value. So we are not losing the unbiasedness property, but we are losing what? We are losing the efficiency, because we know that the OLS estimator is the best. We are dealing with cross-section data. So recall our previous statement that, let me go back. Think about when we discussed this. Okay, we'll see that the beta OLS is blue when the X are stochastic, but we have cross-section data. So in this case, it is still, it's blue, okay? Now, but this is for the OLS case. We are in a GLS world, okay? So we have heteroscedasticity. So what I can prove, what we can say here, is that the OLS estimator still retains the property. It will be still unbiased, but of course it will lose the efficiency, because I mean the variance covariance matrix of the GLS, the standard error I should the correct standard error I should take are the ones that I should take from this variance covariance matrix, but unfortunately I don't know the big sigma. So this would be, the GLS will be the best estimator in this setup. I should take standard error from here, but unfortunately I have not a clue about big sigma, so I cannot go for the best one. So what I can do is the following. I can say, okay, the OLS estimator is still centered, but it will not provide me with the best standard error. So I can run the risk that come back to the T-ratio interpretation. So think about here. So basically I am in a setup where I'm not touching very much the numerator, because the OLS estimator is still, if it is correct, if it is unbiased on the, say, it continues to be unbiased also in the GLS case, but I have some problems here, because the standard error I'm taking here, if they're not the right ones, I'm running a risk, because if the standard error I'm taking are, say, I'm not considering the most efficient estimator. So imagine that I'm taking an estimator of the standard error which is larger than the true one. So I run the risk of having a T-ratio which is smaller than the one I should get. And with a smaller T-ratio, you remember when I said, what is the cutoff? The rule of thumb is if the T-ratio is larger than 2, we say that more or less things work well. We run the risk of having a T-ratio which is smaller than 2, but not because it is actually smaller than 2, but because we are making a mistake here. So when I flag the option, I want robust standard error, I want to fix little bit this standard error, even if I know that with the OLS, this is not, I mean, I should take the best standard error should be taken from the expression from the variance square matrix of the GLS estimator. I don't have the GLS estimator, so what I try to do is to try to correct the standard error I get from the OLS, and that is the robust standard error option. Indeed, let me come back on the point. Now, for the moment, you can take this again, this statement like given. It's possible to prove. Imagine that we have been discussing this. I said before, what is the variance of beta hat given X? It is a matrix, we said. It will be a 2 by 2 matrix, no? And we said that in the classic linear regression model, it is given by this expression, okay? Now, it is possible to prove that if you have heteroscedasticity, the variance square matrix of the OLS estimator in a model where you have heteroscedasticity is given by this expression, which seems extremely complicated. This is horrible. This is nasty expression. Actually, it is not. But the important thing is that this thing here is different from this other thing here. And the point is, so in the model with heteroscedasticity, if I go with OLS, yes, he said you can do that, but you have to quantify the error, the mistake you are doing. You have to be conscious that you are making a mistake. And now we are just discovered, if you believe me, that this expression is the variance of beta hat given X is given by this expression, and you will be convinced. You will see that formally in the next hours, okay, in our next classes. This expression is different from the other one, so I should take standard errors from this variance square matrix, not from this one. And with robust standard errors, Gretel will take standard error from this one, but we need still, this is not yet the end of the story. Why? Because also in this expression, it enters the big sigma matrix that we don't know. So how can I compute this object here? Okay, that is the point. Are you following me, guys, in the reasoning? More or less? Also, Tom, guys. Please let me know if you're not following me. So what we can do, so the point is that I would like to compute the standard errors of the OLS estimator under heteroscedasticity from this matrix. Well, please let me notice that if the big sigma, if you know the very basic ingredient of linear algebra, and if you set the big sigma equal to sigma square epsilon identity, so if you come back to the classic linear regression model, this expression here collapses to the one on the right, because try to put, say, sigma square epsilon identity here, and you will see that there is a big simplification here, because you have inverse matrix, inverse, and I mean, can you see that if I, let me put it, say, identity in place of big sigma, okay? Can you see that this expression would be equal to x prime x inverse? Because I have a huge simplification between this guy with this guy, if big sigma is equal to identity, okay? Now the point is, of course, if big sigma is not equal to sigma square epsilon identity, they will be different. And in a sense, the larger is the distance between this guy here and this guy. You understand? The more heteroscedasticity I have in my data. I'm very intuitive reasoning, guys. Now, how do, I mean, if I want to compute standard error from this matrix, because this is the real variance square matrix of the LS estimator when I have heteroscedasticity, it's not the best one, but it is much better than this, okay? Because this is the variance square matrix of the LS estimator when I have the classic linear regression model. When I have homoscedasticity, indeed you see a single sigma square epsilon. Here I have many, because I have heteroscedasticity, okay? Now, my problem is, how do I estimate this number here? Because x prime x, I know it. It's my data, okay? Now, the problem is I want to focus a little bit on this x prime big sigma x matrix, okay? I want to give you the intuition behind robustifying standard errors. Now, if I have understood that big sigma now is diagonal, with diagonal element on the main diagonal, and if I have understood the link between matrix notation and indexes notation, I realize that this guy here is given by this expression. Sigma square the variances, which multiply regressor, column, regressor, line. But now I'm using the units. This would be a summation from region number 1 until region number 20 of the region. It's a summation. Variance of region 1, which multiply regressor region 1 prime, plus variance region 2, blah, 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 until region 20, okay? The interesting result now is that the US econometrician Albert White had proved the following result, okay? He said, okay, let me take the residuals from the OLS regression. So you estimate, you have heteroscedasticity, you run OLS, and you get residuals, epsilon I at. Please, residuals at because beta at. And beta at estimator is the OLS estimator, okay? Now, what Albert White, and let me say that White is probably the article where Albert White presented this result is the most downloaded paper in economics ever, okay? Because any applied economist at least knows pushing button on Stata or whatever, or any package, the White test. It's a very famous test. And I'm discussing with you in an implicit way the White test. Okay, but just give me time. The result the interesting result by White was the following, that, okay, if you take this expression here, if you replace the unknown sigma square epsilon with the residual squared, okay, and you take an average of this summation, and you have a large sample, so if you send n to infinity, so we need a large sample, so you might argue, well, professor, but we're dealing with 20 regions. I don't know if you can send small n to infinity, but we'll discuss that later on, okay? For the moment, let me send small n to infinity, okay? White proves that this guy is a consistent estimator, so the probability that this term on the left gets closer and closer to the true quantity on the right-hand side, the probability tends to converge to 1. So I am certain, in a probabilistic sense, that my estimator is capturing the right quantity. Okay, in other terms, this quantity here converges in large sample for n that goes to infinity to this quantity. So basically what the message I'm delivering to you is that we have an estimator of, because of White, we have an estimator of this term. So coming back, I said, this is the variance square matrix of the OLS estimator when you have heteroscedasticity is given by this expression. I was in trouble computing this term here, but we just saw that we have in large sample, we have an estimator of the term I'm selecting with my hand. Not the end. The one, we have an estimator for this guy. So I can, basically, I know everything now about this expression here, and I can take standard error, robust standard errors are taken from the main diagonal of the following, of this, the entire variance-covariance matrix. Once I replace, say, the element of the big sigma with the following expression you find here with this guy. So what, at the end of the day, what Gretel or Stata is doing for you is the following job. It takes, let's follow strictly the slides. The consequence of this result is the following. When the econometrician has the suspect that homoscedasticity might not hold in my sample, what she might do, she might do is taking standard error not from this number, from the covariance matrix of the OLS estimator in the classic linear regression model, but it can take standard error from the variance matrix of the OLS estimator in the under heteroscedasticity. So from this expression here, standard error will be computed from this expression here, and these are the robust standard errors, which are also known as white standard errors because of white. And any package, as you have seen, gives you the option, do you want robust standard errors? And now I'm very close to the point. I go back one slide back, and I want to come again on this line here. So you should agree with me that if imagine that I flag the option robust standard error, which means that Gretel takes standard error from this matrix once adjusting for the big sigma, as we said. Okay? And I see that the robust standard errors are very similar to the unrobust ones. So I come back to the point. I estimate a regression 1, where is it? I had model 1 without the standard error option, okay, and I get the following standard error, the following column here. Then I estimated the model selecting the robust standard error option. So what I have done, basically, I have computed standard error from here. In model 1, I had standard error from here. And in model 2, I computed standard error from here. But I have seen that there is not a huge difference between the two. So what's the main message?
Elasticity has been solved.
Can you qualify? Yeah, I understand what you're saying, but you should qualify. You might say, there is another comment by someone else?
Okay, that the model is homoscedastic.
Sorry, can you repeat, please?
I would say that the model is homoscedastic.
Yeah, I would say, you're right. I would say that, computing normal standard error, OLS, and robustifying, I don't have such big difference. So it means, at the end of the day, that probably I don't need to robustify them. On the other hand, if I see that there is a large difference between robust and not robust, I say, well, something is happening in there. And let me say that there is a test that I will discuss with you. I will show you on Gretel after the break, which is known in the literature as white test. The white test for the null hypothesis of homoscedasticity is a test which measures in a statistical sense, the distance between the standard error I have from this part and the standard error I have on the second part. If from a statistical point of view there is no distance, we have homoscedasticity. We don't need to adjust standard errors. But if from a statistical point of view, I see a huge distance, then it means that we have heteroscedasticity. So if we don't have a clue about how to model the heteroscedasticity, I will say something tomorrow on that, I need to robustify, to flag on the standard error option. So after the break, so I promised it's 5 o'clock, we have 10-minute break. After the break, I'll come back again on Gretel, and I'll show you how to read and interpret the white test for homoscedasticity. Now you know what happens, you know the meaning. And I'll come back again. We'll see whether in our model for the 20 Italian regions, whether we need to robustify or not the standard error to make inference, okay? So thank you very much. We make a break and I'll start at 5:10, as promised. 1, 2, 3, prova, 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 prova. Panotto, prova. Non è più silenzioso. We'll see. Okay, so we can go towards say the end of our 3 hours today, and I'm still here to this point. We have quite spent a lot of time on it, and I said, okay, now one way to decide whether we have to robustify or not standard error is to, in a sense, to quantify how close or distant are standard error computed from this, from the yellow one, or from the standard. There is a prime missing here. Sorry. Okay. You discover. I mean, it's unbelievable. You discover typos. So they will be x prime x. Clearly, okay. Or the standard error taken from here. Let me come back on our empirical example, such that you will understand very well what you're doing. And coming back on model 1. Model 1 is the one I estimated without BioLS. And all the time I repeat it several times. I'm doing it now. All the time I click on I estimate OLS. I have in mind a setup where I have homoscedasticity and uncorrelation in the big sigma. And if that is not the case in the data generating process, it means that my estimator has some problems. For instance, we just saw that if I had heteroscedasticity, I go with OLS, I'm losing efficiency. So by robustifying standard error, I'm recovering a little bit the efficiency. But the most efficient one, the efficient estimator, will be a GLS, which is very difficult to compute unless I am in very special cases. Okay. Now, one test. So my first, I run OLS in this model. My first check will be under test heteroscedasticity, and I find white test. So going back, what is white test? I repeat it again. It will be kind of statistical measure of the difference between the standard error I get from this expression here and from this expression here. The null hypothesis we'll be discussing during our program. Look at the program, because we never have to lose. We'll discuss, I'll provide you with very detailed ingredients about testing hypothesis when we are moving here, testing hypothesis and confidence intervals in the linear regression model. But for the moment, what we have to know when we run a test is that when we run a test, we need a null hypothesis, which is the hypothesis we want to investigate. We need an alternative, and we need the kind of tolerance level. The tolerance level is the significant level of the test. And typically, for the moment, we can go mechanical. You will get the you will understand 100%, even more. You have to give me time, okay? But you will understand all that I'm claiming now. We need, say, kind of tolerance level that statisticians call significance level of the test, and the significant level of a test is 5%. Now, coming back to Gretel. So I have model 1 under test, heteroskedasticity. I run white test. So the null hypothesis is homoskedasticity. So all the elements on the main diagonal of the big sigma matrix are the same, against the alternative that the main diagonal of the big sigma matrix are different. There are at least 2 sigmas which are different, at least 2. Okay? And so I click on white test and I get the following estimation output. Now we simply have to focus on this part here. You can forget for the moment about the rest, okay? And the result I got is we'll study the following. We study, okay, when we test hypothesis, we need a null hypothesis. The null could be the individual is negative to COVID. Okay, in our case, will be something. Will be a claim, a statement. The variances are all okay. The alternative, in the example, say the individual is negative. Is positive to COVID. The null was negative. The alternative will be positive. Okay. In this case, the alternative will be heteroskedasticity, and we'll see that when we test hypothesis, we have a test statistic. In our case is 5.22, and this test statistic is a random variable which captures its kind of summary measure of the distance between standard error from here and standard error from here. Okay, and we'll see that all the time we run a test, we get from our package a p-value of the test, which in our case is 0.07. And the mechanical rule for the moment, since we are I'm not yet developing theory of test. You should know something about it from the crash course. I don't know, but we'll come back. We'll discuss it. We'll study it seriously. But for the moment, the mechanical rule is that if the p-value I get from the test is larger than the tolerance level I prefixed before running the test, which was 5%, so 0.05. So since 0.07 is larger than 0.05, I accept the null hypothesis. Or if you prefer, I don't reject the null hypothesis. Otherwise, if I had seen a p-value smaller than the tolerance level I prefixed before running the test, say, imagine that I had 0.03 rather than 0.07, in that case, I would have rejected the null hypothesis. So I was in a situation of heteroskedasticity. You might say, well, Professor, but if I prefix the significance level to 10% in your setup, we still, I mean, the p-value is smaller than 0.10. So if I had prefixed this tolerance level that we'll learn to call type 1 error or significance level, I have to reject the null hypothesis. Typically, people use 5%, but it's just a convention. It's a tolerance level that we'll discuss later on. But from coming back to my phenomenon, what I get from this, from the Y test of homoscedasticity. One thing that, let me remark one thing. Gretel said, this is Y test for heteroscedasticity. Actually, the null we are testing is homoscedasticity, one single variance, and the alternative is heteroscedasticity. Just in words, Gretel calls it that way. So at the end of the day, this result, the fact that I have a p-value which is not very larger than 5%, but anyway larger than 5%, is consistent with what we saw with our what people call A-ball econometrics, okay, which can be very dangerous sometimes. But the A-ball econometrics say, look at the standard error of model 2 and look at the standard error of model 1. They are pretty close. They don't change too much. And we realized just before running the Y test that we are in a situation where we got the intuition before running the test that the two things, that we don't reject homoscedasticity in this model. What is the possible flag in my reasoning? Possible flag is the following one, is that we said that in order to evaluate this object here, in particular, the most selected one, the one I'm touching with my hand, this one, I'm on hand. Let me do like this, elimina. Okay, the selected one, we said I need n going to infinity. Do you remember the result? I need that this guy estimates this object if I send n to infinity. You might say, Professor, you have 20 regions. So you should not run the Y test. The Y test I just computed is a test which holds if you have a large sample, if n goes to infinity. I have n equal to 20, and one question during the first break was, how large? At the end of the day, we are always dealing with finite sample. Even when we are in a big data framework, in machine learning techniques, blah, 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 at the end of the day, small n will be a finite number. The approximation, it's kind of ideal experiment that we do. We send n to infinity. So in this setup, we have to take this information with caution. And I don't have a solution. I simply have to be conscious, aware of what I'm doing. But I'm dealing with 20 regions. Is there homoscedasticity or heteroscedasticity? Difficult to say here. Y test, if we interpret Y test in an extensive way, we might say that homoscedasticity can be reasonable in this setup. Okay, guys? Any question, comments, clarification? So up to this point, we know at least that the first check we do, when we estimate a model by OLS, the very first check we can do is checking homoscedasticity versus heteroscedasticity. And of course, imagine that in this case, if I run immediately the Y test for homoscedasticity, in this case, I would not flag robust standard error because the test seems to say that I don't need to robustify. I don't have heteroscedasticity. So I don't need to adjust I don't need to take standard error. The message is that I don't need to take standard error from here, but I can take it's enough taking from here. Please recall that it is prime here, okay? Yes.
I have a question.
Yeah.
If the sample size is small,
yeah.
Then we cannot estimate by Hertz method the big sigma.
You ask whether we can estimate the big sigma. No, the point is that the point is this, is that we are not estimating the big sigma. We are estimating this thing, x prime big sigma x. So basically, the results proved by the mathematical proof by White is that these things, once you replace the unknown sigma square I with the square of the residual, so this is something that we know. The object I have here on the left is something that I know. This guy is a consistent estimator of this quantity, but I need a large sample. So I'm doing that, but I'm not quite sure that I'm picking out the true quantity. That is my problem. That is the point.
Is there any other option if I don't able to estimate?
The second option is the following. I don't have the blackboard ready now. Tomorrow I'll come back to your point. So the second option is the following: is okay. Imagine that I have good point. I have say, let me come back here. I have the suspect that the 20 Italian regions might be heteroscedastic. Okay. So what I can do is I try to explain. Okay, what does explain the variance of the error region 1, region 2, region 20? So what you might do, you might model directly the heteroscedasticity. Imagine that I say, let me go onward. So 18 should work. So imagine that, say, I have this is my model. Consumption region I is equal, now you need some patience, you have to be patient. So beta 1 constant plus, this is the model we have estimated, beta 2 times, this should be small c, per capita consumption region I, this is disposable income of region I, plus error term. Okay, guys, this is the model, and we have a situation like this. I runs from 1 to blah, 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 until region small n, which is 20, okay? Now, imagine that I say, okay, I have the intuition that epsilon, the variance of the error term, so epsilon square, epsilon I square, okay, so this guy is equal to sigma. Okay. Sigma I well. Sigma square, I do like this, sigma square I, okay? Now, imagine that I have for I which runs from, so I have 20 different variances. And this is more or less the setup I have in mind. So I have almost heteroscedasticity. Now, imagine that I make the following assumption. I make an hypothesis. I say, okay, so according to my view, my theory, my model, I am an expert of regional economics, and I say, okay, the variability of the error, the variance of the error term of consumption, this guy, so sigma square I, is given by, depends on, so I am specifying a model for the variance. I say, the variance of region I is given to a constant, h, where h is a positive number, you understand that? H, okay, times, now, what is the trick, what I can do? I could say, okay, I want to associate the unknown variance to something that I can observe. I could say, for instance, that, well, the variability might depend, for instance, on the square. Look at this hypothesis and let me know if it looks reasonable to you. I say could be the square or square of the disposable income. So according to this hypothesis, I don't know whether it is true, it works or not, but I'm saying that the variance give up to a constant h, depends on the square. Of course, you understand this they will be positive, it must be a variance. So depends on the square of disposable income in the country, which could be reasonable in a sense. Or imagine that you have some observable variable, let me call it, I mean, if you don't like disposable income, but you have some observable variable, let me call it Z high, okay, that you could associate to the, so Z high could be disposable income, but you have some observable variable for which you have observation, which you can associate to the variance, to the variability, okay? So you understand that up to the, and of course this holds for index I, which runs from 1 to 20. What I'm telling now, what is the implication, the main consequence of this assumption? Let me come back on this expression here. If my assumption holds true, I can replace sigma square I with h square of variable z on the first region. Then I have constant h, the square of variable z observed in the second region, and so on. Okay? So I have on the main diagonal now, up to h, up to the constant h, I have observations. Can you follow me, guys? And so let me come back to the, why did I discuss feasible GLS? I did it on purpose. I mean, so at a given point, I have my big sigma. Let me go back to the, yeah, this is the expression of the GLS estimator that you can derive. Now, with my assumption, I can, my big sigma will be scalar h time a diagonal matrix where now I know the elements on the main diagonal because they depend on the data under my assumption. And you will say, well, Professor, but what about the scalar h? That is going to create some problem in the calculation of this guy. No, because of this inverse, you have only inverse here, the h will simplify. Tomorrow I will show you, I will come back on this, I will come back to example. But the point is that under the assumption I'm making, and my assumption is that the variance, the heteroscedasticity depend on some observable variable, I have, at the end of the day, I have a feasible GLS because I can compute this expression here. And if I can do that, I can also standard errors from here. And I'm very happy about that. The point will be, how can I check if my assumption on the heteroscedasticity is good or not? That will be the, I mean, you can do that. You can with this with that assumption, with that, but then you have to, at the end of the day, your decision will be, okay, am I really capturing the heteroscedasticity with my model? That will be the $1, the very important question that to solve. Okay. Tomorrow I will provide you a very concrete example with the maths and blah blah blah. Okay. I mean you, the class. Did I satisfy your curiosity, more or less? Yeah. Okay. Any other question? because I mean we can use the last. I still have to use. I cannot stop here, unfortunately. We have to. I still will take 10 minutes of your time. Okay, so I'll do that. Opening, going on with our program. We have a tight program, unfortunately. So coming back to the point now, what I'm doing now is we are more or less closed. We still need to close it, but now I'm moving to properties. You say, but you've been already discussing the property of the LS estimator, not in a formal way. I've given words. Now I'm giving you some more concrete details. So I'm moving to the properties of the LS estimator in the classic linear regression model. And otherwise, if I don't cover this in the proper way, you're not going to understand anything about 6 testing hypotheses and confidence and computing confidence intervals in the linear regression model. So let me start just something about properties of the LS estimator in the classic linear regression model. So what I'm doing now, I'm moving here. So number 5, properties of the LS estimator in the classic linear regression model, and now we come back to case 1, big sigma like this, which is the case that we can manage. You see that all the time we deviate from that, we have to invent something about on how to deal. And so in this case, we already said we have k plus 1 unknown parameters. We have the slope parameters in beta and the single sigma square epsilon. And we know how to estimate that. And we know that the LS estimator beta is given by this expression here. And we know that the estimator sigma square epsilon is given by this expression here. And we know everything up to this point. Yes?
Question about 1 over n minus k.
Yeah?
But is that why we are losing a degree of freedom?
Yes. Yes, exactly. In order to compute this estimator, the estimator of sigma square epsilon depends on beta, okay? And to estimate beta is k by 1. So we have estimated k elements. That's why we want to we divided by that. But this explanation is, let me say, I don't like it. The point is that if you divide by n minus k, and you are in a small sample, and you have cross-section data, if you divide by this number, the estimator of sigma square epsilon will be correct, will be centered on the true value. Otherwise, it will be not. But you understand that if n is large, if you are dealing with 20 million, million Italian households, divided by n on n minus k is equal to 2, 3, doesn't matter. It is important in small sample. If we are dealing with 20 regions, in our example, 20 regions, we have the beta, we have 2 parameters. One thing is if you divide by 1 over 20, and one thing if you divide 1 over 18. It makes a difference, but it's not an important one. Now, we focus in a very strict sense about the properties of the estimator beta hat. Beta hat is a random variable because it depends on x and y, where we have random variables. And we now, up to this point, we know very well that if we want a good estimator of the true beta 0, where I call down with beta 0 the true unknown value of beta, we study 2 objects, basically. The expected value of beta given x, this is a bad way of going, okay. The expected value of beta, the estimator given the matrix x, of course, by using the law of iterate expectation, we can compute also the unconditional expectation of beta. We are interested that this one is equal to the true beta 0 or not. And then we achieve, today it was a class on variability at the end of the day. We need to compute to know this variance covariance matrix. So the variance of beta given x. When we compute standard error, you are seeing that we are conditioning on the x's. The standard error depends on the regressor, on x. That's why I'm conditioning on x. Okay? Why do we focus on first moment and variance? Because the unbiased in a finite sample, the estimator will be unbiased if I have this condition, and you would like to have this variance covariance matrix as small as possible, and this is the efficiency condition. Now, and then I will stop here. In order to discuss, to derive this condition and also to give you the expression for this variance covariance matrix, we need to do the following, an algebraic exercise, which is the following one. So this is the beta OLS estimator. What I do now, I plug in, I replace the y with what? If this is the model evaluated at the true beta 0. So what I'm doing now, I'm plugging in, I'm replacing y with this expression. So I get, by doing that, you can see that we have, say, x prime. So I replace y with this expression here. Okay? And now what I do, I go on in the next two lines just with the algebra. There is nothing mysterious in linear algebra. There's nothing mysterious in the next two slides. For instance, two lines, sorry. What I'm doing now, I multiply, what I've done, first step, I multiply x prime x beta 0, I get this expression here. And then I go on x prime epsilon, I get this. Linearity. Then I go on, I have this object, these terms, which multiply this plus this. And in algebra, this is the property of commutativa, associativa. Or it's a property of linear algebra. What I have to do, I have to multiply this guy times this, and I have the first object here plus this guy here times this, and I have the second term here. I'm applying in a very mechanical way basic rule of algebra. So what I'm doing is complex? No, it is linear. Nobody can claim that the rules of this rule of linear algebra are complex. They are mechanical rules. And now you should agree with me that here I have, say, x prime x inverse times x prime x. So I have A inverse times A. So I have the inverse of a matrix times the matrix. I got the identity, and that's why this product here collapses. What should I select for selecting? Oh, okay. And now it's clear. I have understood. So this product here, the one, well, it's not very manageable. Anyway, okay. Let me come back to the end. The end is that this product here, the one I'm touching and selecting in my hand, will be identity. By construction, inverse, okay? And the second term, it remains like this, okay? Now, and I will stop here, promise. So, look at this expression. The beta at estimator is equal to true value plus something, okay? Now you should agree with me that the properties of the LS estimator will depend on what happens to this something here. There are cases where when we can kill this object here, think about, do you remember my very first claim this afternoon was when we were discussing blue, I said, here's the point. B hat is blue when X are not stochastic, very seldom, very rare case in social science. So then I will stop, promise. Let me go to the case where X are not stochastic, but are deterministic. Where is it? My expression is this. Now, look at this expression. Bit hat is equal to true value plus this object. Now, if I take expected value of beta on the left, it will be equal to the expected value of this term on the right? So, the expected value of true value beta 0 will be beta 0. And then I have the expected value of the following quantity. But I say if the x's are deterministic or not stochastic, I can shift the x's from the expected value. So I end up with the expected value of epsilon. What is the expected value of epsilon? 0. So we have just proved in 2 lines that if the x's are deterministic, the expected value of beta hat is equal to the true value because the expected value of epsilon is equal to 0. It's not difficult proving this. It's a very simple thing. Now, tomorrow, we are moving to investigate. You will see that tomorrow it will be very useful for us working on conditioning on the x's before moving, because it will be crucial, conditioning on the x. Of course, we condition on the x when we have random variables among regressors. When regressors are deterministic, we don't need to condition on regressors. Okay? So thank you very much for your attention. Tomorrow we are still in this room or elsewhere? This room? Okay, I will check on the table. Thank you very much. I stop here. I can stop registration. Okay, stop it. Fatto.
Thank you, bye.
Thank you very much. Thank you very much.
Thank you, goodbye.
Goodbye. See you tomorrow.